We're starting a new idea here in section 9.5. We're going to be solving trigonometric equations. I find it a little bit more interesting than just the plugging and chugging of the last section. So the first fundamental idea here is that we're going to solve to find an angle of theta. So sine of theta is going to equal something, for instance, like 1/2. Now we're going to say, okay, what angle equals 1/2 when we try to solve this? Now, what we have to keep in mind is that we have multiple angles. So remember, every time we spin around the circle, we get the same value. So every time we spin around and around, we get the coterminal angles that all match the same value. And it wouldn't matter if we just went around this direction. We could also go around 360 degrees or 2 pi the other direction. So what this is telling us is that we'll get a value, but we have to keep in mind that we could keep, I think it makes more sense if you wrote it like this. They're trying to say the same thing, but we could spin around the circle over and over again. And the k represents every trip around the circle. You can multiply that by, k could be 1. You took 1 lap around the circle. 2, you took 2 laps around the circle. So unless they define for us that we want to be just 1 trip around the circle, we have to be careful because there's really an infinite amount of solutions. Now, excuse me, let me show you this in a more practical way. I want to know the angle that has a cosine ratio of 1/2. Well, if I look at my unit circle, that's easy. It's pi over 3 and 5 pi over 3. So remember, this is a 60-degree reference angle. So cosine is, what quadrants are we in here? Yeah, this is in quadrant. Cosine is positive in the first and the fourth. So that's how I got these two values. 60 is the reference angle. So pi over 3 and 5 pi over 3. But it wasn't defined where. It's any value that has 1/2. So we have to spin around the circle over and over again. So again, I don't know why they write it like this. I like 2 pi k better. But what they're saying is you could keep taking laps around the circle in either direction, and all the coterminal possibilities would also be true. So both of our solutions that they found here, they tacked on the 2 pi k, plus or minus, because you could go around clockwise or counterclockwise. Okay, so let's look at it again. So I'm just going to look on my unit circle and say, hey, what angle has a value of 1/2? Well, we're talking about sine here. That's a 30-degree angle is my reference angle, and it's a positive. So I want quadrants 1 and quadrants 2. Well, here's my two values, pi over 6 and 5 pi over 6. But we could keep spinning around the circle, so we tack on that plus 2 pi k. Now here they did it like that. I'm glad. Okay, so plus or minus the 2 pi k. Now what's different here is we're going to solve a real equation. It's going to involve a little more than just, we're not at the end already. And this is going to work the way any equation would work. If I were talking to you through any equation, I'd say, hey, where's the difficult portion? Well, it's the cosine of theta. So let's solve it down to the difficult portion, just like we would. So if this was 2x minus 3 equals -5, we're going to follow all the normal rules. I'm going to add 3, divide by 2. So we've seen this before. Hopefully that makes sense to you. So I'm going to add 3, divide by 2, and now I get down to cosine of theta equals -1. Okay, well, let's look that up on our unit circle. That happens at only one unique place. It happens when theta equals pi. Now, what about spinning around the circle, though? There are the coterminal possibilities, so shouldn't we add this? Well, typically we would. Typically we'd add on that we could keep spinning around, but sometimes the problem will say, hey, I just want you to tell me the values on one trip around the unit circle. This is just one trip around. Well, if that's the case, pi is the only value. We don't have to do it on this one because they told us to limit it to one trip around the circle. Okay, let's follow this idea again. So if this was 2x plus 1 equals 0, we would get x by itself. Well, we're going to get the difficult portion alone. We're going to get sine of x alone. So we have 2 sine of x equals -1. So sine of x is going to be -1/2. Okay, now we get a sine value of 1/2 when we have 30-degree angles. So 30-degree, and our reference angle is pi over 6. So you are reading this off the unit circle. I'm just trying to do this in my head here. So sine is pi over 6. Now, but we have a negative 1/2. So when is sine negative? In quadrants 3 and quadrants 4. So I'm going to use this reference angle, but I want the values of sine that are in quadrant 3 and 4. So this would be like 6 pi over 6 would be halfway around. This would be like 12 pi over 6. Again, you're just reading these right off your unit circle, but I'm trying to derive these because I don't have the unit circle in front of me. So my values are 7 pi over 6. I'm going to add that reference angle here. I'm going to take it away here, and I also have 11 pi over 6. Again, you just read that. Now, do I have to add the plus or minus 2 pi k? Not this time, because it said just give me one trip around the circle. So here are my values for x. Okay, same thing here. I don't know that there's anything different about this problem. So, yeah, oh yeah, okay, well we do have this. So it's sine squared. So we get the difficult portion is the sine squared. So I'm going to get him alone. I send the 1 over, divide by 2. Now, here's what's a little different. We don't want sine squared, we want sine. So I'm going to square root both sides. Just as if I had x squared as 1/2, I would square root both sides. So that's going to get me down to sine is plus or minus 1/2. Well, let's simplify this. If I have a fraction under a square root, it's the same as the square root of 1 over the square root of 2, which is just 1 over the square root of 2. Rationalize that by doing radical 2 over radical 2. So here's what I get. All of this is the same thing. Oops. All of this is, I'm looking for a value of sine because I've square rooted it. That's equal to plus or minus radical 2 over 2. Well, when does that happen? That's pi over 4 is our reference angle. 45 degrees is when that occurs. But because of the plus or minus, we want values of sine that are plus or minus. I want all 4 quadrants. You following that? What angle has a sine ratio of radical 2 over 2? Well, that pi over 4 is the reference angle. But because it's plus or minus, we want when the y's are positive or when the y's are negative, that's all 4 quadrants. So we're doing all 4 of the values off the unit circle. And again, we were limited to 1 trip around. We don't have to keep spinning because they told us we could stop 1 trip. Okay, they gave us one here involving cosecant, but the trick to that would be, let's turn cosecant into 1 over sine. That's what it is. And so I don't want to try, I don't know the values of cosecant. They're certainly not on my unit circle. So if I turn it into sine and solve it here by sending the sine up and the negative 2 down, I get this, which I think we've already done this one. So this is a 30 degree, which is the same. Pi over 6 would be my reference angle. But I want it to be negative. So I've got pi over 6, and that puts a negative sine is in quadrants 1 and 4. So here are the values in quadrants 1 and 4. Now, here's the only little twist that they put on this. They wanted it between 1 and 2 trips. You see this is 2 trips around the circle. So for 7 pi over 6 and 11 pi over 6, all I did was I added. Now I've rationalized the denominator. Do you see what I've done here? But this is really just 2 pi. I've just taken another trip around the circle. And that's where these values came from. So they wanted me to be 1. I could go around once, or I could go around twice. They were happy with that, but no more. Okay, tangent 1. These are a little more difficult because you're dealing with the fact that tangent isn't on your unit circle. So right away, where are we here? What are they doing? Okay, yeah, I don't like how they're explaining this, so let me do this. Okay, so I have a weird angle in here, but I just want I don't know what it is, but all of this is equal to 1 at some point on my unit circle. Well, what is that? When do I get a tangent that's equal to 1? Well, that's at pi over 4. So remember, tangent is sine over cosine. And sine and cosine have the same value with a pi over 4 reference angle. They're both equal to radical 2 over 2. So if I didn't remember that, I would just go around my circle and remember that tangent is sine divided by cosine. So if I need two of the same identical value in order for this to equal 1. Okay, now you could think of this in two ways. This is going to happen, tangent is going to be positive in quadrant 1 and quadrant 3. Do you remember that discussion? So, but another way to do this would be the period for tangent is just pi. So here's what I've got so far. I know this is a weird angle, but I know this is true at pi over 4. Now, you can work this two different ways. You could do this. It's also equally true at 5 pi over 4 in the third quadrant. Okay, now what's different about this one is we're not done. Before we would do this trick and we'd be finished. But we had a weird angle in there. We had theta minus pi over 2. So we're going to add that pi over 2 over to the other side. We'll do it on both of these. Okay, you need a common denominator now, so that's 2 pi over 4 plus pi over 4. This is 2 pi over 4 plus 5 pi over 4. Okay, so I've got 7 pi over 4, and what do I got here? 3 pi over 4. Okay, let me talk you back through this one. So I know that this is a weird angle, but I'm just going to solve it. There's some angle, even though it's very strange, that equals 1. Well, that's pi over 4 and 5 pi over 4. Now, I'm limited to one trip around the circle, so I've got the only two possibilities here. Now, we're not done. This was equal, theta minus pi over 2 equaled pi over 4. So I have to just solve for theta by sending pi over 2 to the other side. We haven't done that before. We work the two values, and we get our two possibilities are 3 pi over 4 and 7 pi over 4. Okay, now real quickly here, I think this is probably the better way to do it, but suppose you had just solved pi over, like done this version right here. Because tangent has a period of pi, you could have just taken this answer and then added pi to it, which would be plus pi, which would be 3 pi over 4 plus 4 pi over 4. That you could have got the answer this way too, the second answer. Just because tangent has a period of pi, we could have gotten the quadrant 3 answer doing like this. Anyway, I don't want to lose you there and make this more confusing. Just that we had two, it's probably easier to think of it. We had two possibilities off our unit circle where tangent was 1, and then we just had to swing the pi over 2 to the other side. Okay, so where is tangent equal to radical 3? So I would think of it like this. I would divide the two values on the unit circle. Remember, it's sine divided by cosine. So on your unit circle, it's cosine and then sine. And I would divide those. And here's the choice that would make this equal to radical 3 over 2. Or radical 3. So I need a time when sine is equal to radical 3 over 2 and cosine is 1/2. Well, that happens with a reference angle of 60 degrees, which is pi over 3. Okay, so the value of x that makes this happen is pi over 3. You could also look this up on your unit circle and see that it happens in quadrant 2 or quadrant 3 as well. So remember, tangent is positive in quadrant 1 and quadrant 3. So if you look up on your chart, you're going to get negative radical 3 over 2 divided by negative 1/2, and that's going to get you the same thing. So we've got two values. X can be pi over 3 in quadrant 1. Or it could be 4 pi over 3. Okay, so here are two possibilities, but look what they did. They didn't restrict it. They didn't say that we can just spin around one time. So what we need to do here, remember the period for a tangent function is just pi k. So all we have to do is just add this plus pi k on here, and I see that I've made a mistake. Because the period of tangent is pi k, I don't really need this one. So if there's no restriction, if this had said go one time around the unit circle, if it had said between 0 and 2 pi, then I would have given them these two answers. But because they left it open-ended, I need every possibility. And because the period of tangent is pi k, I don't really need to list this one. It's true, it was right. But if I add this pi k on here, it's going to have covered that one as well. So I didn't need it. So I hope what I'm saying makes sense. It is true that pi over 3 and 4 pi over 3 both solve this equation. But because it didn't say anything about one trip around, I don't really need to say this again because I have to add this on. And this covers 4 pi over 3 and every other possibility. Okay, one last idea here. They're going to ask us to just punch these on our calculator to solve them. It's not very hard. So we would still do the same thing. Oh, no, not yet. I'm sorry. I'm getting ahead of myself. So what we're going to do here, we just have a more complicated one. So imagine that this was 2x plus 3 equals 5 plus x. What we're going to need to do is we are going to need to distribute here. We're going to need to get all the x's back together. So the first thing they did is they distributed this too. We're going to try to get all the tangents of x back together on one side. So let's see if we can do it. We send the 2 through. We've got this line. Now let's get all the tangents on the same side and all the numbers into the other, just like we would solving any equation. Now tangent of x it's like a big I don't know. I've got 2 tangent of x's here minus 1 there. Well, I can combine them just like I could combine 2x minus 1x. Same thing. So I get tangent of x equals negative 1. So we've done all of this, and we're now looking for in what location does tangent of x equal negative 1? Well, we saw we get 1 with pi over 4, and tangent is going to be negative in quadrants 2 and quadrant 4. Now, we've talked through the logic of that. I hope it makes sense because cosine, you'll have one sine or cosine that's negative in those quadrants. That's why that happens. Okay, so if we look up, just read it off our unit circle, and we're going one time around the circle. That's all they're asking for us to do. There are 2 locations where I would get negative 1. So again, you're dividing the sine over the cosine. You're dividing radical 2 over 2. You want it to be negative, so it's quadrants 2 and 4. You'd find this. If you divided the sine by the cosine in those 2 quadrants, you'd find it's 3 pi over 4 and 7 pi over 4. All right, now here's the calculator thing. So this is pretty straightforward. There's only one little twist here. So I just would use inverse sine here. If I want to solve this, I've got sine of theta equals 0.8. Just make sure your calculator's in radians. So sine is going to get me 0.9273, and we know that we could spin around and around the circle. Now they've also solved this in degrees. If you switch this over to degrees, you'd multiply it by 180 over pi, and you'd get 53.1. But here's what they're saying. The angle 53.1 is a positive value of sine, but the calculator didn't give us that. And the reason it doesn't is because, remember, inverse sine is limited to the first and the fourth quadrants. Do you remember this? We had to restrict it. So there's a value in the second quadrant that would be acceptable, but it didn't show up on our calculator. So what we're going to do here is 53.1 is a reference angle. I could use it as a reference angle. We don't usually use those because they're not our standard angles, but it could still be a reference angle. I could then put 53.1 over here in quadrant 2, and if I did that, that would be the second value of sine that would give me that result. So they're just taking 180 minus 53.1 because it's a reference angle. They're just This is 180. They're subtracting to 53.1. That would give me this angle here. Now, I know this is confusing. Let me talk you through this again. So this part's easy. Just make sure you're in radians. I do the inverse sine. But inverse sine was restricted between pi over 2 and negative pi over 2. Do you remember we had to restrict it? So we are getting, the calculator is only giving us values in the first and the fourth quadrant, but sine could be positive in the second quadrant as well. So I thought of this value, changed it to degrees just by converting it here. And I thought of 53.1 like a reference angle. And if I think of it like a reference angle, the second value, the second angle that would get the same value of sine in quadrant 2 is 180 minus 53.1 or 126.9. Okay, needlessly confusing, but I hope that made some sense. I hope. Okay, so we would do the same thing. So I would do inverse cosine of negative 0.2. Now I'm assuming this is in radians. And I would get 1.77. Okay, but like they did on the last one, we're going to change this to degrees. If I would convert that, I would do multiply it by 180 divided by pi. And I get 101.54 degrees. Now, cosine, we did an inverse cosine, and that is restricted between 0 and pi. So we need, where else? So this was a negative value of cosine, and our calculator is only giving us one in quadrants 1 and 2. So we also need quadrant 3. Cosine is also negative in quadrant 3. So my angle here is 101. So this is complicated, but think of this as a reference angle. That's 101, so the reference angle would be 180 minus 101.54. So we're just going to call that 79. Well, I guess it's 78.5. Do you see what I'm doing here? I'm finding that reference angle. Now, I also need a value of cosine in the third quadrant. My calculator didn't give it to me because it can't, because of the restrictions. So I'm going to take this reference angle and put it into quadrant 3 by adding it to the x-axis, by adding it to 180. So what do I get here? So another possibility is 258.5 degrees. Okay, I know that's confusing. That seems like it should be an easy question at the end, but hopefully you followed my logic there.